All right, let's jump straight into today's explainer. We're going to explore the secret life of Azure, and to do that, I want you to imagine stepping into a grand Victorian library right in the heart of London. Picture this. A junior colleague named Timothy is working there, and he notices a really frustrating pattern. Their incredibly advanced AI librarian is giving out factually perfect answers, but the scholars, well, they're constantly sighing, looking totally annoyed, and just immediately retyping their questions.
Timothy completely hits the nail on the head here. He points out to his senior colleague, Margaret, that sure, the machine knows exactly where every single piece of information is hidden in the library, but it's completely missing the scholar's actual intent. It's technically right, but it's tonally deaf. It's literally one of the most frustrating things to interact with a genius system that just entirely lacks the nuance of an actual human conversation. Now, Margaret, who's the senior software engineer, knows exactly what this condition is called. She explains to Timothy that their genius system is essentially trapped in what's known as the static plateau. Think of it as a state of frozen logic. Yes, the system is incredibly smart, but it has absolutely zero memory for its conversational mistakes, and because of that, it completely fails to get any smarter from its interactions with the users. It's just stagnant.
So, that brings us to a massive engineering challenge. How do we actually give a genius system a memory for its conversational mistakes? Well, the solution is to map out a continuous route directly from the scholar's terminal and literally loop that data straight back into the heart of the library's main system.
And this illustrates beautifully how they're going to break out of that static plateau. They're going to use a real game changer, RLHF, or reinforcement learning from human feedback. Instead of just dumping more raw facts into the system, they're creating a continuous feedback loop. Basically, they're letting the machine learn directly from the humans who are using it, which aligns the model's behavior with actual human intent using preference data.
Section 1. 2 kinds of signals. Capturing the scholar's thoughts. Now, what's super interesting here is the stark contrast between the 2 kinds of signals the system can listen to. On one hand, you have explicit feedback, your standard thumbs up or thumbs down ratings. But let's be real, those are actually quite rare. Most people just don't bother to click them. The real treasure, the absolute goldmine of data, is implicit feedback. This is the behavioral data that users leave behind without even realizing they're doing it.
Let's look at how the system actually reads these implicit cues. By measuring things like dwell time and user actions, the AI learns a ton. If a scholar gets an answer, accepts it, and stops searching, boom, the system registers that as a massive win. But if the scholar reads the answer, sighs, and immediately rephrases their query to try again, Margaret calls that a silent no. The system quietly captures these silent no's to figure out exactly when it failed to deliver a satisfying tone, even if the underlying facts were totally right. Of course, tracking all this behavioral data means privacy is absolutely crucial. Before any of this data is used to improve the model, every single captured signal is instantly anonymized. The identity is just completely stripped away. The system is built to learn what kind of tone and structure is preferred, absolutely not who preferred.
But right here, Timothy brings up a brilliant point. He asks Margaret, wait a minute, what happens if the crowd collectively decides they just hate a factually correct answer? If we're training the AI based on human preference, do we literally let them vote away the truth?
Section 2. Guardrails on human feedback, protecting the truth.
To stop the AI from turning into just a crowd-pleasing liar, the feedback loop has to have incredibly strict boundaries. Human preference is only allowed to refine the tone, the style, and the helpfulness of the response. It does not touch the facts. Truth and citations are verified by a completely separate approval gate. Those facts are strictly non-negotiable. No way around it.
On top of that, they protect the system by rate limiting the feedback from every single scholar. I mean, think about it. You definitely don't want one obsessive user spending all day trying to train the AI to speak in their own quirky, specific way. By rate limiting, Margaret guarantees the AI learns from the broader wisdom of the crowd, rather than just getting hijacked by the loudest shouter in the room.
Okay, so with all this explicit and implicit feedback safely gathered and our guardrails firmly in place, we get to the actual mechanics. How do we take all this raw human behavior and turn it into a mathematical engine that truly improves the model? Section 3. The reward model compass, steering the AI.
To build this compass, the system relies on rigorous A/B testing. They present senior scholars with 2 totally different versions of an answer to the exact same prompt, and then ask them to rank which one is better. By harvesting these expert preferences, they literally build a mathematical compass. This compass then automatically teaches the underlying AI which conversational direction we humans actually prefer.
But here's the kicker. They don't just blindly accept every piece of ranking data. To keep the model from getting entirely confused by conflicting opinions, they enforce a consensus threshold. They toss out the low signal noise and only use the preference data when there's clear agreement among the humans. Specifically, we're talking about a 70% agreement rate or higher. If the humans can't agree on which answer is better, the AI just ignores it.
Section 4. The maturing library. Continuous fine-tuning.
Now, this isn't just some quick one-and-done patch. It's a continuous monthly cycle. Every single month, the system rounds up the top-ranked interactions that pass that 70% consensus threshold. They take that pristine preference data and use it to fine-tune a brand new version of the AI. The approval gates handle the facts, but this feedback loop, it teaches the AI what is actually better. Through this cycle, the system matures way beyond just acting as a frozen database.
So, what's the ultimate payoff of all this work? Fast forward a month later, and Timothy watches a scholar approach the terminal with a wildly complex question about pre-industrial economics. The AI librarian responds with incredible nuance, perfectly acknowledging the scholar's specific interest in trade routes. And the best part? The scholar doesn't sigh. They don't furiously rephrase their question. They just nod, save the response, and walk away satisfied. The system finally listened to how the user wanted to be spoken to. This continuous learning is the magic that truly bridges the gap between raw, frozen data and genuine human connection. It perfectly sums up Margaret's realization. The smartest system in the room is the one that knows it still has something to learn from the people it serves. So I'm going to leave you with this thought to ponder. As our AI systems become vastly more knowledgeable than we are, is their ultimate test of intelligence not what they know, but how well they can learn to understand us? Thanks for hanging out with me for this explainer, and keep asking the right questions.